presented by the Construction Safety Committee and our friends at SACO. Webinar is going to be approximately an hour with time for questions at the end. When we get to the questions session, please use the text box and we will call you on first come, first serve there. We are always looking for new members of our group. So if you're interested, please email Nico Swart, which I'll include in the text box, and he'll get you on our future invites for our monthly meetings. If you need a PDH certificate, we're going to be offering a 1 hour certificate for people who use the professional development hours. Please send me an email and I'll have them out to you within the next week. I will also include my email in the text. Today, we're going to be discussing a typical geotechnical report structure, interpreting exploration logs, soil index properties, typical report findings, including red flags, and then typical report recommendations of what they mean. Our presenter from SACO is Brian Reed, who's a graduate of the University of Arizona and a senior geotechnical engineer with Smith & Nalla Engineering. He has over 20 years of experience, geotechnical engineering experience, including performing, reviewing, and coordinating geotechnical investigations. Mr. Reed has provided these services for a variety of projects, including commercial, residential, industrial developments, power plants, water treatment plants, hospitals, educational facilities, highways and bridges, and soil retaining structures. As a senior geotechnical engineer for SACO, Mr. Reed conducts geotechnical analysis, prepares and reviews soil and foundation reports and specifications, reviews and provides technical supports to engineers, technicians, and construction personnel, and assists with project management. So I'm going to turn it over to you, Brian, to take the lead and go from there. And we'll leave, like I said, questions at the end, and then I'll help Brian out with calling on order as they come up. If you should see a text box. If you're not familiar with Zoom, you do have a little function at the bottom that says more. And if you click on that, it'll allow you to select the chat and you can kind of pop it up from there. Okay. Thanks, Brian. And I'll let you get started.
Oh, thank you, Adam. Assume everybody can hear me. So if not, send me a message, but we'll get started. So as Adam mentioned, I'm Brian Reed. I'm with SACO, Smith & Nalla Engineering. I was going to talk about a contractor's guide to geotechnical engineering reports. The goal of this is kind of a rough overview. I'm not trying to get too deep into the woods on reports, just give you guys, as most of you are contractors, I believe, kind of a flavor and a little bit of understanding of what I do and what I'm trying to communicate to you guys on a geotech report. So about SACO, Smith & Nalla Engineering Company. We were started in 2011. We're locally owned and operated. We have offices in Tempe, Southwest Phoenix, West Phoenix, primarily servicing the Palo Verde power plant, and then Tucson. I'm down here in Tucson. Our founders, the principal engineers, Mike Smith and Michael Anala. We were founded to service clients and keep safety as a priority. Right now, we have about 40 employees. That's engineers, geologists, field laboratory technicians, special inspectors, and administrators. Yeah, that's a little about SACO. About me, like Adam said, I got my bachelor's and master's of engineering from the University of Arizona in geological engineering. I'm licensed in Arizona and California, and Adam listed a whole bunch of stuff. And yeah, I've done residential, commercial, and there aren't too many projects I haven't attempted to work on over the years. A little bit of everything. It's been quite the journey. Most of that's on the consulting side, but I've also done some design work on temporary excavation shoring, temporary slopes, and on MSE, mechanically stabilized earth retaining walls. Occasionally I've done a handful of soil nail projects and tied back excavations as well. on the design side of things. All right, so I want to get into, here's what I'm going to talk about today. I want to start with some common terms that you might see in a geotech report and hopefully explain some of the jargon you might see. Give you guys a typical report structure, just an overview of what most reports look like. I'm going to go into logs, boring logs or logs of explorations, and show you some typical things you might see on most reports. An overview of soil index properties. These index properties can help you understand what kind of issues or what kind of soils you'll be dealing with on site. Some typical findings in a report, common red flags, unsuitable soils or difficult soils, and potential excavation conditions and how to figure that out. And then kind of the typical recommendation you see in most reports, how most geotechnical engineers deal with some of the findings and some of those problem soils that we run across the site. So yeah, we'll start with common terminology. So these are pretty common things you'll see in a report. There's others, and feel free if you want to add comments, questions of terms that you run across in reports that you don't know what we're talking about. I might be able to explain that. But I'll just start. So fill. Anytime I talk about fill in my report, I'm talking about uncontrolled, unnaturally deposited materials. So this could be anything from landfills and construction debris to soils that have been compacted and moisture conditioned and compacted, but we don't have a record that those soils were properly tested or properly placed. So fills are kind of a red flag. I'll get into that later in the report. Native soils, I refer to them as native soils. Sometimes you'll see them as alluvium, or these are naturally deposited materials. These were deposited by stream flows or wind deposits, or even materials, rock that's weathered in place. These are naturally deposited soils, and generally that's what we're running across in most sites. When I talk about engineered fill, I'm talking about fill materials that have been placed in a controlled manner. So these are moisture conditioned soils, compacted soils, and importantly tested soils. So kind of needs those three things for me to consider it engineered fill. You need to moisture condition it, compact it, and then most importantly, at least in my mind, test it. Someone hopefully can sign off that it was compacted and placed in a controlled manner. In the Southwest and kind of Tucson, Phoenix, the basins around the southwestern part of the state, we have collapsible soils, and these are soils that can support a load, a building, a foundation, as long as they remain dry. But if moisture contents change, if they get wet, they can settle a lot. I've seen corners of buildings settle 6 inches or a foot relative to the rest of the building. So a major red flag, and that's one of the more typical conditions we're looking for, or that's one of the conditions we're looking for when most geotechnical engineers are performing soil reports in the Southwest. And then the other red flag, bad actor, are expansive soils. These are clay containing soils that change volume with response to moisture content. So they shrink when they dry out, they swell and expand when they get wet. And we don't have the worst expansive soils in the country, but they are present here. Typically these will impact more lightly loaded structures, unreinforced floor slabs, interior walls, occasionally even lightly loaded foundations. They usually don't have enough swell potential to pick up an entire building or cause issues like that. Those are issues you often see in Texas and in the Front Range of the Rocky Mountains, the Denver kind of I-25 corridor. We don't usually have issues like that. A few pockets here and there, but by and large, the soils are not expansive soils aren't a major issue. So let's go into an overview of kind of a typical report. I'm going to use a SECO report template, but most of the reports I reviewed follow a really similar format to ours. So usually you'll see an introduction, a description of the project, some description of the investigation, what was done, and then a summary of the findings, some recommendations. Those recommendations include recommendations for civil engineers and the structural engineers on how to design the buildings for the site conditions we found. And then they also contain the recommendations for contractors, so the earthwork recommendations, compaction, import specifications, all those fun things. So, and then limitations, what are the limits of the report? What did we look at? How did we look at it? And then usually an appendix, a site plan showing where we did our explorations, a log of the explorations, and then any lab testing, summarize the testing. So a couple of flags, just to be aware on the project description. That's an important one to review when you get a soils report. Make sure that that description in the report matches your project. This really isn't as big of an issue on a municipal project. Well, sometimes it is, but I definitely see it on the private side. A landowner, a developer's got plans, they get a soils report, they sell the property to a different developer. They have different plans, but they use the same report, and now you've got different conditions. We do generally tailor these reports to the project. So if it's switching from single family residential to a tilt panel warehouse, we're going to provide different recommendations and different findings at a different level of investigation. So just make sure that the description in the report matches your project. And likewise on a treatment plant expansion or something, there may have been an original report done that maybe doesn't match the conditions, or maybe doesn't match the new construction that's going on, and that may be a flag for you guys to raise and say, this doesn't match what our current project is. Do we really have the information we need for this from the soil side? And the other one I want to point out is limitations. Geotechnical engineers, we work kind of similar to doctors in the sense that we're providing an opinion based on somewhat limited information. I've got an excerpt from a court case defining the standard of care, level of care, and this is what we're striving to meet: a standard of care that someone else in the industry with the same information would hopefully come to the same conclusions. That they would be performing the same level of investigation, the same level of lab testing, and hopefully with the findings from that come up with similar conclusions. And a lot like a doctor, I can't guarantee, I can't warranty that my findings are 100%. Just like a doctor can't guarantee you outcome of a surgery. At least they shouldn't be, right? No doctor is going to tell you you're going to live to 95 if you have this surgery or don't have this surgery, more than likely. So just keep that in mind on the geotech side. We're limited to our understanding of the site, and therefore our recommendations and everything else are based on that. So next step, we're going to get into exploring the logs, interpreting the logs in the report. So here's kind of the cover page. You'll often see these. You'll often see these symbols. You'll see a page like this at the beginning of the log or the end of the logs as sort of a summary, and explaining the samples that you see on the log, some of the symbols of the logs for the samplers, and symbols for the materials. And then you'll see a second page, often with the USCS, the Unified Soil Classification System. This is the system that geotechnical engineers use to classify soils. It's based on the gradation and the plasticity index of the materials. So There's a pretty extensive flow chart that we follow to come down to this classification, and you know the GCs and the SCs and all of those symbols. That's where this comes from. It comes from this classification system. There's an ASTM for it. You know, there's an ASTM for that that you guys can review, or anybody can review if you're curious. You know where this comes from. I'll get into a little bit with some of the symbols and some of the flags that these symbols, you know, that you should be flagging when you see some of these soil types on your site. There's a definition here on particle sizes, just the different classifications, the terminology we use for, you know, when you see boulders on a log, or when you see gravel on the logs, or sand, what we're talking about in terms of size of material. So that's often explained on this key. And then relative density, these are all based on the blow counts, the standard penetration test. The standard penetration test is defined as an 1.5 inch inside diameter sample that's driven into the ground with a 150-pound hammer falling 30 inches. So we basically drive this hollow tube into the ground using this hammer, and we count how many blows it takes to drive it 18 inches with each 6-inch increment. So, and we add up those last two numbers, and that gives you the end value. Often there's some correction factors and a few other things thrown in there. Most reports in Arizona just provide the raw end value. There's no corrections on there or anything else. But this gives you a rough sense of the relative density just based on blow counts. And you'll see on the left hand of that column that the arrow is pointing to, it's sand and gravel is relative density. And then cohesive soils, these are fine grained soils, clays and silts, are in terms of consistency. And you can see the terminology used. So on the next sheet where we get into the logs, you'll see where we use the term medium dense, and that just ties back into the blow counts. So that's just a relative density on there. There's a bunch of stuff on the logs. The logs are very information dense. There's a lot of information on the logs, and it's not necessarily the most obvious what we're trying to say without getting a little bit familiar with it. Everybody's logs are a little bit different. This is a typical SACO log, but the information that we're providing is pretty much on all the logs you're going to see. They just may present it a little bit differently. I know I've seen some of the other companies present their blow counts graphically. They just have a chart that shows the blow counts. Some of them describe things slightly differently, but all in all, they're about the same. So on this one, I've got a note on here about fill. Whenever you see fill soils, we talked about that. That's kind of a red flag. Uncontrolled soils, those are usually not suitable to remain on site. So if you see fill, it should be a red flag. You should go back up into the report and look at those recommendations closely and see what it says. What am I supposed to do with this fill material? Can it stay on the site? Is it full of trash? Is it going to have to be hauled off? What do we need to worry about with this fill material? If you see high blow counts or really low blow counts, you need to be worried potentially about high blow counts are going to indicate dense soils that can be hard to excavate. Low blow count soils are loose soils, so that may require over excavation, or could be material that's not suitable for bearing for foundations, or could be difficult to excavate in terms of stability. You may have to work a little harder to keep a trench open, or keep that excavation open for you to install underground features. Back on the previous page, I showed the different symbols. There's two types of samples typically driven, and we drive ring samplers. That's the upper one, the upper arrow, and then the split spoon, or I'm sorry, the standard penetration test is the X with the two shadings. That's our symbols. If you'll go back to that symbol page, I'll back up and show you. Maybe I don't need to do that, but back on this symbol page, you can see where the different symbols show up, the sampler symbols. So the one that's half shaded, that square, is a ring sample. That sample is a almost 2.5 inch inside diameter. And that sample is filled with 1 inch tall brass rings. The brass is maybe a 1/16 of an inch thick. When we drive those samples into the ground, we often can get an undisturbed sample, and we can take that sample back to the lab and get densities or do some additional testing on it. The standard penetration test, the SPT, it's a smaller diameter, and that sample that comes out is considered disturbed. And then the other samples that we'll grab, I call them bulk samples. Some engineers call them grab samples. This is just cuttings, basically auger cuttings, or in the case if we're doing explorations with a backhoe or an excavator, we'll just take excavation spoil, and those are completely disturbed samples from the site. There's no real sense of density because you're just grabbing the material. So those are the different samples you might see on the logs. Let's see, go back to where I was. All right, so that was the logs. I think I missed one thing I was going to talk about on the logs real quick, and that was termination. So when we get to the bottom of the boring, if we've reached our planned depth, we'll get a note that just says bottom of boring, or you'll see some kind of termination note. But occasionally, we'll run into materials that we can't drill through. Those could be oversized materials. Up in the valley in Phoenix, the sand, gravel, cobbles along the Salt River are pretty tough to drill through with auger drilling. There's cobbles and boulders mixed in that stuff, and we just can't drill through it. Sometimes we hit bedrock. Sometimes we just hit really highly cemented materials we can't drill through. So anytime you see a termination note that says refusal or something that impeded full exploration, that's something to be aware of, especially if you've got sites, relatively shallow refusal, things of less than 10 feet. If you're installing sewer lines at 25 or 30 feet deep, and none of the borings could get that deep, you've got a problem. Partly because partly you just don't have the information of what the subgrade is like, and also we couldn't auger through it, so you're going to have a tough time digging through that. If you see something like that and know you have a sewer that's going deep, or you have something that's going deep, you get on the phone with the engineer, the geotechnical engineer, and with the owner, and come up with a plan on how are we going to get this information. That's kind of working blind. So yeah, look for termination notes as well on the logs. That's all I had on the logs. Like I said, they're rich with information. I didn't get into everything on those, but that's the basics. That's probably 90% of what you're going to see on a boring. So let's get into the soil properties. Again, I'm not going to get too deep into this, but talking about the dry densities and moisture content. The dry density is that's the weight of the soil without factoring in the moisture, because the moisture content varies. We just want to know how much soil is in a cubic in the US in a cubic foot of soil. So how dense is that? The moisture content is useful information when you're trying to figure out how much water you're going to need to add to get for compaction, or are you over the moisture content for compaction? You're going to have to dry this out. It's going to be problems. Plasticity index is kind of a sense of how sticky that soil is. I talk about the liquid limit and the plastic limit. So the liquid limit of soil is basically where it begins to behave like a liquid. Once you get enough moisture into it, the soil begins to flow. The plastic limit is basically where it behaves plastically, where you can mold it and squeeze it. And the difference between those two is a plasticity index. So keep an eye on the liquid limit, especially trying to compare it to your optimum moisture content on a Proctor. As those two numbers get closer and closer together, your soils are going to get harder and harder to work. And the same with a plastic limit. Where is that relative to the current moisture content? Going into sieves, the sieve analysis is basically just the distribution of the grain sizes throughout a given sample. So I kind of talked about that on the logs, where we define the different sizes. So if it's bigger than 3 inches, it's a cobble. If it's bigger than 12 inches, it's a boulder. The difference, the cutoff between sand and gravel is the number 4 sieve, which is about 3/16 inches in size. Gravel, I think, are deceptively small. Gravel looks, to me, it kind of looks like coarse sand. So when you see things described as gravel, 3/16 isn't a very big particle. So just keep that in mind. Gravels range all the way from 3/16 to 3 inches. So it's a pretty broad range of size. And then the other ones you'll talk about are the fines. Those are the materials finer than the number 200 sieve, which is, that opening is about twice as thick as a human hair. So anything that passes through that is silt or clay. The USCS defines clay as something that has plasticity, and silt is something that doesn't have plasticity. So that's the only difference. The particles are, they're roughly the same size. Clay particles are generally smaller than silt, but I'm not splitting hairs at that point. And then I've got a note here at about 30% fines. When a sample has about 30% fines, or your soil has about, or more, it begins to behave more like a clay or more like a silt. It doesn't take a lot of fines to really impact your the behavior of the material. Kind of mentioned this, higher fines, higher plasticity are generally detrimental to soil behavior. So start seeing numbers greater than 30 on the fines, you start seeing plasticity greater than about 10 or 15, it should be a note that in the back of your mind, these might be a little harder to work. And when you start seeing, fines greater than 50% and plasticity above 20, that really should be a flag that you're gonna have a hard time working these soils. And they're probably gonna have, they're going to have difficult or poor engineering properties. And then I kind of mentioned this too, comparing the in situ moisture content to optimum moisture, the fines content, and the plasticity index. So as you start seeing in situ densities, the in place moistures, if they're getting close to optimum or above optimum, or if they're approaching liquid limits, these are soils that are wet and they're going to cause you problems. You're going to have to figure out how to dry them out, or just count on they're going to be difficult to work. Soils begin to pump. I don't know if you've ever seen that on trying to compact soils that are really wet, and they then have a high liquid limit, and they start moving around on you as you're trying to compact them. It becomes a real problem to deal with. And then on the other side, coarse grained soils that don't have a lot of fines and no plasticity, kind of beach sand, those can be hard to work for opposite reasons. They don't have that binder in them to keep together. So, you tend to just kind of shove them around and push them around, and it's difficult to compact them and keep them compacted. So just note, soils that have less than 10% fines and PI less than 5, those could be equally difficult to work and difficult to excavate. You've all tried to dig a hole in the beach and dry sand, I'm sure, as a kid, and remember, for every scoop, out, a half a scoop or more comes back into the hole. It's kind of the same issue. You're gonna have to lay those flatter. You're gonna have to figure out how to keep a hole open in that stuff, and it becomes a challenge. We don't have real clean sands out here generally, but there are some parts, especially if you get out west around Yuma. There's some really clean sands out there that are very problematic to deal with. I talk about swell here. So this is the swell potential. This is the test we use to figure out if the soils have expansive properties. We generally provide it as a percentage. Usually, we're trying to mimic field conditions. So you're recompacting that soil. We're going to compact it in the lab and try to get it near optimal moisture content. And then we put a weight on it and we saturate it or inundate that sample with water, and we just see how much it picks that load up, how much movement we get. So what happens is the clay is absorbing water, and it ends up between the minerals, and it ends up inside the molecules actually, and that's how the expansion happens. Usually 2% is kind of my cutoff. If you see more than about 2% swell, it's probably material that shouldn't be used on site, at least not underneath lightly loaded structures or structures sensitive to movement. To find another way, either remove those soils from the site and replace them. They can also be chemically stabilized. We can add lime or cement to those. But they're best avoided underneath lightly loaded floor slabs, structures like that. Yeah, I kind of just said this, but usually if you can put some confinement under it, and when I say confinement, heavier foundations, heavy footings usually have enough bearing pressure to compensate that swell. The soils don't have enough pressure to pick up something excessively heavy. It's really under the slabs and stuff that's a problem. So if you can bury the expansive stuff under a couple feet of non-expansive material, that can take care of it too. I know I've been asked, it's possible to blend non-expansive soils and expansive soils to try to get something suitable, but it's really tough to blend soils, especially because the expansive soils are clay, and it's hard to blend a clay in a manner that you don't end up with lots of clumps, and you kind of end up with balls of clay mixed in with sand. And it doesn't really work very well, but I won't entirely rule it out. But if you ask me, I'm gonna frown. And then occasionally I see this a lot on sites where the top couple feet is expansive, and then you get non-expansive stuff below it. So something you might want to look to in the logs or ask the engineer, a geotechnical engineer, is if you've got a couple feet of expansive stuff on the near surface and non-expansive stuff below it, you may be able to flip the site or segregate those fills and put them deeper and use the non-expansive stuff in the near surface underneath floor slabs and underneath the pavements, and use those soils so you don't have to export export and import. You don't have to waste that material from the site and bring new stuff in. I'm going to go over findings, kind of common red flags, unsuitable soils, and excavation conditions that we run into. So common red flags, the two things, like I mentioned earlier, we're looking for are collapsible soils and expansive soils. Those are probably the most common red flags you're going to see in a soils report. And those are the things I'm looking for most of the time. If I check those off, if I find collapsible soils or I find expansive soils, they're common enough. We know how to deal with them. But those are the main things I'm looking for. And don't be surprised if you see them, but take note if you see somebody, if you read the report and it talks about collapsible soils on the site or expansive soils on the site, those are very common, and they're certainly, I would say they're certainly not deal killers on a project. They just need to be dealt with. Less common stuff is when we do hit uncontrolled fills. This is really an issue with redevelopment sites. If you see auger refusal or test pit refusal, recognize that you're going to have a difficult time excavating on the site. You may be in bedrock, you may be in cobble. I mean, it could be anything. It's definitely worth focusing on that in the report and trying to understand why, and trying to understand how that's going to impact your site. We don't hit groundwater very often in Arizona. That's not surprising, but occasionally it happens. There are a few pockets that will hit it, and be aware. Whenever you see clay on the boring logs, lean clays or fat clays, or silt, those are fine grained soils. They're difficult to work. Very often the clays are the problem with the, they're going to be expansive. But mainly they're just a workability issue. Trying to compact clay is a real pain. They take a lot of water to get to optimum moisture content. And then when you get there, they pump and they move, and they're real difficult to work. So be aware of clays, be aware of oversized materials, just both from difficulty in excavating and the difficulty of trying to reuse that material as fill. We generally, most of my reports recommend you segregate out that oversized material. Anything bigger than 3 inches, I don't really like to see reused on site. It's too difficult to work around. Not to say that I'll never let that happen, but it's usually going to require some extra observation and extra testing and a lot more care in placing it. And then similarly, I talked about poorly graded sands or well-graded sands, just because they're prone to caving, they're difficult to compact, and there's something else to look for. I'd said this earlier, higher fines and higher plasticity are detrimental to soil behavior, especially when you get moisture content, or moisture increases. So some of the things, could be a seasonal issue too. If you've got a site that's got a lot of fines, got a lot of plasticity, it might be fine when the weather's dry and we don't have any rain. But if you try to work those in the winter, during our winter rains or during the monsoon, if we ever get a monsoon, those soils suddenly, now they're wet and become a big issue to work with. I'd mentioned this before, looking at the in situ moisture content, optimal moisture fines. Take a look at that, see where things are landing. If you see a lot of moisture in the soil, or it's starting to approach some of those index properties, you need to be aware that that could be a difficult soil to work with. We talked about the beach sand issue, and then getting to know the USCS, the Unified Soil Classification System. Lean clays or CL, fat clays, CHs, silts, ML, those are difficult soils to work with. And then conversely, the poorly graded sands, the well-graded sands, and then the dual classification ones, the well-graded sands with clay and well-graded, poorly graded sands with silt. Those can be difficult to work with also. Just again, they don't have enough fines, they don't have enough binder, the term used, to make it easy to compact. Excavation conditions. So generally, if we can auger through it, you can usually dig it with conventional equipment. That's not always true, but usually, if I can reach 15 or 20 feet with my auger, you can probably dig to it. But just be aware, you see cobbles and boulders, you see notes about hard drilling or slow drilling or cementation, caliche. Those are things to be aware of. Most of the auger holes are, 7-8 inches in diameter. So we can drill, right past a boulder or a cobble or a chunk of concrete and not even know it. So, I do my best if I see evidence of that to note it in the area, but we don't always hit it. So just keep it in mind. But if you do see notes on the drilling logs about any of those conditions, be aware. It could lead to problems down the road. Same with the blow counts. You can start seeing high blow counts, something more than 40 blows per foot on a standard penetration test, or higher on a ring sampler. That's something to keep in mind. The blow counts on a ring sampler are usually about twice the same of a standard penetration test, and that's just because the ring sampler is a bigger diameter. It's kind of like driving a finish nail versus a framing nail. One's a lot harder to put into a 2x4 than the other, and it's just because of the diameter of the nail, and it's kind of the same with a ring sampler. It's almost a 3-inch diameter sampler, and a split spoon's maybe half that. So the blow counts are changed accordingly. So I tried to make it clear on the logs and the blow counts on my logs when you're looking at a ring sample versus a standard penetration test. I know sometimes where you just get a graphical representation of the blow counts and you don't actually get the blows. I don't know that that's always corrected for. So be aware if you see a sudden drop or a sudden increase, check the sampler type and just make sure that increase isn't a result of just a different sampler, and the effect on that diameter. And then same thing on the logs. Anytime you see refusal on exploration, it should be a red flag that you may have difficult excavation conditions. It's on a case-by-case basis. Obviously, if you're only going 5 feet deep and refusal is at 15 feet across the site, then it's not as big of a concern. But if you hit if they're hitting refusal, prior to your planned pipe invert, or the bottom of your footing, or whatever it is you're building, know those last few feet are going to could be a challenge, or may not even be possible. Ripability, I'm going to kind of sidetrack a little bit here. If we do hit a lot of refusal, there's some other tools in the toolbox that can be used, and one of them is seismic refraction. And this is a geophysics method where we can get the seismic velocity. I know Caterpillar has this ripability. This is the chart from Caterpillar, but I know there are other manufacturers that have ripability charts tied into the seismic velocity. This information comes from a seismic refraction study. If you've got a site where you're going to be in a lot of difficult excavation, you might consider doing a seismic refraction, because it gets you a big area of survey, probably much less expensive than trying to use alternative drilling methods. Normally when you see refusal, it's refusal to auger drilling. There are other drilling methods that can be used to get through cobbles and boulders and rock. There's a bunch of other methods that we can use, but they get expensive quickly, and often limit the kind of sampling that we can do, and a few other things. And some of those other methods, we can't even get material back. We can't even recover the material to actually look at it to tell you what we're drilling through. But like I said, geophysics is a nice method to give you kind of an overall view of a site, and tie into these ripability charts and give you at least a better sense of are you going to be able to excavate this, or with conventional equipment, or are you going to have to go to something specialized, or are you into possibly drilling and blasting, or something else, and can approach your project appropriately. So the last thing I'm going to get into are recommendations, kind of the typical recommendations you see, why we recommend that, and kind of geotech specs. So typically, and I'm going to go over the major ones you see, are collapsible soils and expansive soils and fill. So collapsible soils is almost always why you'll see over excavation recommended. So the reason we over excavate is that collapse potential is coming from the soil structure. There's nothing really inherently wrong with the structure. It's just the way it's been deposited on the site. So usually you can take that material, excavate it, moisture condition it, and recompact it, and you get rid of that collapse potential. And so usually we're doing two things with over excavation. We're eliminating the collapse potential in that area that we've now turned into engineered fill, and the trigger for collapsible soils is usually an increase in moisture content. So now if you've got a cap of engineered fill, that's usually quite a bit less permeable than the soils around it, and that cap kind of helps resist moisture from getting into the collapsible soils that may remain below it and activate it. So you'll see collapsible soils a lot, or you'll see collapsible soils, you see a recommendation for over excavation, and that's usually why. I will put a flag out. I feel like lately on a lot of geotech reports I've reviewed, I see over excavation as sort of the default position that a lot of geotechnical engineers have taken, regardless of the site conditions. So it's a reason to go back and look at your logs. If you're seeing really high blow count material, if you're not seeing any real explanation as to why they think they need over excavation and they're defaulting to it, I think it's worth challenging an over excavation recommendation, just if you don't see a reason for it otherwise. Like I said, I've seen a lot, and lately on sites that really don't need it. And I'm not sure why. I think there's a certain level of, I'm not going to throw anybody under the bus, but there's a certain level of ease if you just say over X and you're safe, maybe. I think that's why you're seeing that. When you see expansive soils in the site, usually the response is just going to be remove and replace with non-expansive materials. Usually that's limited, usually under the floor slabs or the exterior flat work. So if you've got a site that has a lot of it, and that gets, obviously it's going to get very expensive to remove and replace that, consider chemical stabilization, adding lime, adding Portland cement, to avoid having to import a bunch of material. Existing fills, usually when there's fill on sites and it's uncontrolled fill, my default position is to remove it and replace it. If the fill material is suitable for reuse, great, have at it. Obviously, if it's full of debris and material, it may be more cost effective to just remove it from the site. Those are sort of the typical recommendations you're going to see. Some of the specifications, I generally try to allow you and allow the owner to leave the on-site materials on-site to be reused. I recognize that that's the most cost-effective way. Sometimes to do that, especially if it's slightly expansive, we'll put a little bit more strict moisture control on the moisture specification and on the compaction side. Whenever you've got expansive soils on the site, one of the things that really helps is to keep those soils moist while you're waiting to build your slabs or build your foundations. If you can keep the moisture in those, keep them from drying out, the expansion potential is greatly reduced. Part of the problem is, the clay soils with expansive soils is the pads get built and then they sit for 6 months and they dry out, and then they build the slabs and they're on bone dry soils, bone dry clay, and when those clays get wet, they really expand and cause problems. So take a look at those compaction specifications. It may allow you to keep material on site that's less than optimal. And then I'm pretty relaxed on what you bring in for import. But again, if you're going to spend the money, make sure you're bringing in good stuff. Don't bring expansive materials in. Don't bring in clays and fat clays and silts. Avoid really coarse grained stuff and avoid oversized stuff. That's pretty common sense, but just take a look at that kind of stuff before you go bringing in soils and making a bad situation worse. That's all I've got. It covers just about as far as I think we can get into in the time we have. I'll open it up for questions if there's anything. And yeah, thank you for your time. Hopefully you learned a little bit on here. So I know I didn't want to get too deep into things, but at least give you a flavor of what we're thinking and how we come up with these recommendations.
Well, thanks, Brian. If somebody has a question, please put your name in the chat and we'll call on you, and then Brian can take your question. I'll let you go ahead and speak in the mic and ask Brian some questions here. I'll get the I'll start out here. We already got somebody popped up. David, do you want to unmute your mic here and go ahead and have at it?
CPT versus SPT test. What is the most common here in Arizona, and which would you recommend, let's say, for a large building?
So I don't usually see CPT testing is cone penetrometer testing. I haven't seen a lot of cone penetrometer testing, at least on a drill rig. Geotech investigation performed out here. Usually our soils are just too dense for it. Now you may see the hand-driven DCP, the dynamic. Is that what you're talking about? The hand-driven one, or on the back of the drill rig?
The back of the drill rig.
Yeah. I mean, those just normally we don't do those out here. That's more of a kind of coast-wise. I'm not going to say I've never seen it done, but it's pretty rare to see CPT testing done in Arizona. Partly just our soils are too dense and they just can't penetrate through. So most of the time you're going to see the SPT, standard penetration test, and that's going to be supplemented with the modified, the ring sampler that I talked about before to get undisturbed samples. So there may be some firms that are running CPTs, but in Arizona, but I haven't seen too many test results. I haven't seen too many reports with cone penetration testing.
Okay. And I don't know if somebody else has another question, but I have another one.
Oh, go ahead.
So on the SPT test, you count the blows on the soil, right? So every time you blow the soil underneath will compact and it will create some stress and a stress cone. The machine does account for that as it goes down, like, or I mean, it wouldn't really affect because it's very light. I don't know. I'm just trying to figure out as you go deeper and the more you blow, there's a stress on the soil underneath, and I wonder if that probably give you, or there's a chance to give the run readings. I'm sure you know the answer. That's why I'm
sure.
asking.
Yeah. So just to explain, and for those who aren't familiar, so the standard penetration test, normally we run hollow auger. So it's basically, I mean, it looks like a pipe with flights. So it looks like a pipe with a screw. We'll drill down, and usually we drive a sampler every 5 feet, sometimes a little more frequently, but normally every 5 feet we'll drive that sampler. The sample is driven a total of 18 inches, and we count the blows in 6-inch increments as we drive that sampler. The first 6 inches of the test is disregarded, and then we add the last 2 6 inches together, and that's how we come up with the end value of the blow count. So this test, I think, has been used since like the 1920s, maybe earlier. It's been used, gosh, all over the world. I think that standard penetration test, you can see it performed in just about all over the world. And as far as the increase in stress, I mean, occasionally we'll see blow counts increase from the first the second 6 inches to the third 6 inches. That's pretty typical, but not always, and that's generally accounted for in the test. So it's partly, I think we're only driving that sampler that 18 inches. The further you drive it, the higher those the skin friction, the soil catching on the sides of that sampler slow it down. So if you drove it 18 inches and then turned right around and drove it another 18 inches, you would start to see an effect from that. But generally, the test is small enough, the drive is short enough that we don't see a lot of effects from that. It's an open, it's a split barrel sample, so the inside is open. So the soil, really the only area we're talking about is just the thickness of the steel around the tip. So the initial, you see a major impact from sort of in place densification as we drive that sampler. So does that make sense?
Yep.
Okay. Anything else?
Hey, while we just wait here, if there's any more, can you explain the process for like sand cones and nuke gauges? I know I got some younger engineers on our projects out here. If you can explain how that works, when you're nuke
Sure.
using getting densities and kind of talk about that a little bit.
Yeah, so basically those two methods are a way to test the in-place density of fill material. The nuclear density gauge uses a radioactive source, uses two sources. I forget the exact elements, but it uses two sources, and it's basically just a Geiger counter. You drive a hole, you put that source down in the hole, and then you expose it, and then there's a detector back in the gauge. And the more dense the soil is, the more radiation is absorbed by the soil, and so the lower the count, the lower the count of radiation you're going to detect. And the same with water. The other source is absorbed by water, and so the more moisture in the soil, the less radiation reaches that detector. We take that gauge, we calibrate it in the morning. There's called a standard block that we set it on that is calibrated, and every morning we check the count of those two sources, and then so that's one way of testing the density. It's pretty straightforward. It's a lot easier. The second way, the sand cone test, is a little more complicated. Well, it's a little more effort. It's maybe easier to understand though. With a sand cone, you're digging a cone-shaped hole. You're carefully removing all the soil from that hole and setting it aside, and then you're going to fill that hole up with sand. And the idea is, the density of the sand that goes in that hole. You know how dense it is, and the volume of the if you know the density and you know how much sand is in there, then you know how big the hole is. And if you know how big the hole was and you know how much the soil that came out weighs, then you can infer how dense the soil was. I don't know if I explained that very well or not, but did that make sense?
Yeah, and you typically use that, right? I know we have like a rock correction factor, right? When we got
Correct.
material that's got a lot of rock and it's thrown off the nuke gauge, right? So it's
Yep.
just something to be aware of for engineers. You got some rocky material, right? It's going to throw off your densities. So I know on a project that we had for Maricopa flood control, right? We had to do this sand cone on a daily basis just to recalibrating our nuke gauge, right? To make sure everything was good. We had some rocky kind of bony material, right? So that's a project Seiko and PCL was on.
Yeah, and then comparing that back, so the soil density is, if you guys are familiar with the Proctor test, that's basically a laboratory test to determine the maximum density of the soil and the optimum moisture content. So as you add moisture to soil, it compacts. It gets easier and easier to compact. The water kind of acts as a lubricant. At some point, though, that water becomes a detriment to you. It starts kind of pushing the soil away. So as you change the moisture content, you get a parabolic curve, and there's some point where you get a maximum density at a certain moisture content. And that's the maximum density and the optimum moisture content. And so we take that test. Usually we specify the contractor needs to get at least 95% or some percentage of that maximum density from the lab. And so that's what we're holding the U2 on the compaction side, and then we're using the nuclear density or the sand cone testing to compare those two. So we're looking at the density we got on the field versus some percentage of the density we got from the lab, and we're hoping that you're 95% or whatever the specification is. Sometimes it's 95, sometimes it's 98, sometimes it's 90. It just depends on what the material is being used for. But that's what we're checking. So and when you start getting problems, between those, one of the things to check is make sure you're using the correct Proctor on the correct material. The materials are matching. Make sure that there's not an issue. Nuclear gauges, they malfunction. That's part of the reason you do a sand cone correlation. It's a chance to double check that nuclear gauge is working. It's kind of a black box. You're pushing a button and hoping the numbers are coming out right. There's not really a way to check that they're the numbers are correct. So that's where, doing a sand cone occasionally or side by side and making sure you're getting, similar results is why you would do a sand cone and a nuclear density test. So those are some of the things to consider when you get into the field testing.
Do you need to have those recalibrated? I know they get recalibrated, right? How often? What do you have? What's the procedure for, if I have an engineer on the job site and is just checking everything as a part of our QC plan? Those nuke gauges need to be, I assume, calibrated on a yearly basis. And what do you do there? Do you send them back to a factory or the manufacturer, or what do you guys typically do over at SECO?
Yeah, we have a third party that calibrates our nuke density, the gauges. Partly it's a radioactive source. If you guys are familiar with anything radioactive, has a certain amount of decay on it. So those gauges do have an expiration date. Those sources are pretty powerful. The half-lives on those are pretty long, but eventually a gauge will lose, it's losing radioactivity every day. And so they do get calibrated once a year. And really technically every morning we're checking it with that standard block. We're recording what that count is in the morning. And sometimes I'll even do it, midday just to make sure that we're on. But, like I said, it is kind of a black box in the sense that, we can't really do anything but trust the detectors picking up the radiation, and so they are checked, but if you start seeing issues, I'd say it's rare that it's the machine, that it's the density gauge, but I'm not going to say it never happens, because it does.
What are and last, I guess, I don't see any more questions here, Brian, for you, but what are the safety precautions using that? It's radioactive. What are your safety precautions that you use for those?
So, yeah, it is radioactive. The safety standard we follow is as low as reasonably possible as far as exposure goes. The sources are in the tip of that gauge. You should never see the tip of the gauge. If the technician's running it right, they have a template that they use to drive that hole in the ground, and then they pull the template away. They use that template to set the gauge on the ground, and then they extend the probe into the hole. That if they're doing it right, like I said, you should never see that tip exposed. When the gauge is closed, there's a cover over that tip, and then further, the source is encased in at least 2 or 3 layers of material. So it would be quite a challenge to get that material opened up and be directly exposed to the source. They're embedded in a bunch of stuff, and then there's a ton of regulations that we have to follow, of course. If you ever see them, you see the technicians, they pull it out of that box that's inside of another box. It's locked twice inside the truck or to the truck. There's at least 2 locks. There's a bunch of rules we have to follow. They're generally really safe. I don't think I've ever heard of anyone being exposed to a source, and even if for some reason that source is exposed, we're not talking about, there's not a lethal amount of radiation in there by any means. Certainly if you were exposed every day to it, it would be a problem. But, there was a time when technicians used to have to, wear dosimeters to measure their exposures. And, and I think that may have been the case when I started. Nobody wears dosimeters anymore. Nobody's checking that because there just hasn't been any exposure to it. So they are very safe. Obviously it is a radioactive source, so we want to be careful and we want to keep everybody safe. But yeah, those are the major safety thing is probably the bigger safety issue is they're heavy, because they are encased so much, and we probably have more guys getting hurt picking them up and moving them than have ever been to exposed radiation.
Great. We had another question pop up from David. It was just any other options for density testing besides nuclear?
Sure. So we mentioned the sand cone. So that's one option. Those are probably the two most used. There's supposedly one of the manufacturers of density gauges has come up with a different method. I think they use, it's either an electrical source or a magnetic source. I can't remember, but they do have they have been playing with another method. Everyone in the industry would love to go away from nuclear density gauges. The regulations and everything else, they're expensive. They're expensive to maintain. The regulations are an absolute nightmare. And so we would all love to stop using nuclear density gauges, but they're the fastest, easiest way to get density. So that's why we use them. But yeah, the sand cone method, in the geotechnical side, I can drive a sample into it and get a relatively undisturbed sample. It's not always possible in every soil type, but I can, just like during a typical investigation, I could drive one of those ring line samples into your fill or into the soil and take it back to the lab. Obviously that's slow. I gotta get it back to the lab and I take it apart, trim it up, and then oven dry a sample for the moisture. But that's certainly a way to do it too. It's just a lot slower than the density gauge, which is the other reason why they're so prevalent. Is just it's quick. You know the answer pretty much immediately. Even a sand cone, I can get you the density. The moisture content's a bit more troublesome to get the moisture content of the soil. I know we've had microwaves on site. We got a generator and we're running a microwave and we're heating up the soil to drive off the moisture to figure out the moisture content. You guys may have seen a speedy moisture meter before. A speedy uses calcium carbide. Calcium carbide reacts to water, and it produces it actually produces acetylene gas. It's kind of interesting, but anyway, you take the speedy and you add a little bit of calcium carbide and you shake it up really good, and you measure the pressure on it. They're not the most accurate, but it's a way to get the moisture content sort of instantly. I've also seen a really accurate balance in a test tube, and you take a little bit of soil and heat it up in the test tube and drive the moisture off that way, and you weigh it wet and you weigh it dry. None of those really are as super effective as an oven dried moisture content, but they get you in the ballpark relatively quickly, so you can tell if you're at least on the moisture side, because you got to get the moisture content to determine the dry density, because all of those densities are based on the dry density of the soil, not a moist soil. We need to factor out the moisture content in there. So there's not a lot of great options for soil density beyond nuclear and sand cone.
Yeah, so we got another one here. His last question from David is when a modified Proctor test is beneficial over a standard, and why one over the other? So
the standard Proctor, the only difference between the two Proctors is essentially the amount of energy that goes into the sample. So a modified Proctor, when you come to the lab, if you ever swing by the Seco lab in Tempe sometime, and you can see the difference. But a modified Proctor hammer is a bigger drop. It's a heavier weight. It's a bigger hammer, and we compact it in the mold with more blows, more lifts. So there's a lot more energy. Can't remember the difference in numbers, but there's a lot more energy that goes into a sample from a modified Proctor. And so there's no real advantage to one over the other. Often what ends up happening is if we use a modified Proctor, we'll often reduce the required density. Instead of trying to get you to 95% of the maximum dry density that we would on a standard, we might say, well, you need to get to 90% of the modified Proctor. So it's just a different hammer size. It's kind of standard of practice. Arizona, we generally, most places are going to use the standard Proctor. It seems like California, maybe in Texas, most people use a modified hammer. The reason or why, I really don't know. But one just using more energy than the other, so you're going to get a higher density from a modified versus the standard Proctor. It's definitely worth paying attention to that. If you see modified in the spec, be prepared. You're going to have to probably put more energy to get compaction as compared to the standard Proctor. But and the only reason they get more dense soils is, like in the case of a dam, which I believe is where the modified Proctor was originated, was in California on flood control projects. More dense soils they're less permeable. So you're going to get less moisture running through them, less chance of water going through them. You've got more soil in there and less air, so it's more dense, it's more compact. So, but it just seems to be a local practice dictates one or the other. I don't think one is better than another. It's just recognizing that one has got more energy than the other. And in the end, we're probably going to require, we may relax some of the compaction using modified Proctor versus a standard Proctor, and you probably end up in about the same place in terms of density. So that makes sense?
Yeah.
All right.
All right. So I want to thank everybody once again for attending, and thanks Brian for giving a great presentation. Also want to thank Mike up for IT through AZ Water for helping us get this set up. Like I said in the chat box, it has Nico. If you're interested in joining our construction safety committee, you can contact through AZ Water through the construction safety. If you'd like to attend some upcoming meetings, or email Nico directly, he'll get you set up. And then I originated setting up this meeting, so my email is obviously in the chat or on the web page where you signed up, and you can send me an email if you need a PDH certificate, and we'll be giving out one of those upon request for an hour for attending the session. So I want to thank everybody for attending once again, and have a good day. Thanks, Brian.